We might ask now, what if I want to improve my approximation? I want to answer this closer to the actual area under the curve. I have two options. I can use more and more rectangles, or I can pick a shape that fits the curve a little better. So we could use more and more rectangles. I think that's obvious how you'd go about that. You just chop the rectangles so that they were narrower. Notice here, this is a picture of a left-hand approximation. Here's the right-hand approximation. What if, instead of using rectangles, which either happen to always overestimate or always underestimate this curve, what if I connected the left corner and the right corner and I made trapezoids? So I'm going to zoom this in. Do you see that I'm using trapezoids to try to fill in the area under a curve, but it's still a curve. So there are these places here, there's still a little bit of error, but you can see that the error for each trapezoid is much less than either of the rectangles I could have chosen last time. So that's another technique we could consider using. We could find the area under a curve, approximate the area under a curve by adding up the areas of trapezoids, which most of the time will fit closer to the curve compared to any kind of rectangle that we might choose. We've reviewed this a little bit already. Remember, in geometry, you found the area of a trapezoid by averaging the parallel sides and then multiplying by the distance across the other dimension. So usually that was the top and the bottom you would average, and then the height you would multiply by. In calculus, when we're going to use these trapezoids to approximate area under a curve, we're going to find that they're going to stand on their end instead. So our parallel sides are going to be the left and right side. They're going to be vertical, which are the two heights, the two function values. So we're going to average those two heights and then multiply by the distance across. So average of the heights times the width. This is the formula that you're going to be using more. So let's try this one. We're going to go back to finding area under a velocity curve to compute distance traveled. I've been asked to use a trapezoidal sum this time with 4 subintervals. And again, they're not going to try to trick you on the AP test. If there are 4 subintervals, you'll be able to come to your table, and there are 5 data points. That means there are 4 subintervals. So from 0 to 2, 2 to 5, 5 to 7, and 7 to 10. And I'm going to draw in the trapezoids for you this time. Our goal is to eventually be able to compute a trapezoidal sum without making the picture. So check it before I move to make a picture. My time is measured in seconds. So those are going to be the widths of the trapezoids. And the heights of the trapezoids are going to be the velocity values. They're all measured in feet per second. So I'm going to have an average of 2 velocities, so feet per second, which are the heights. I'm going to multiply by the width, which is measured in seconds. That is going to give me areas, seconds times feet per second. Areas measured in feet. I'm going to add up the areas, and my answer is going to be in feet. And that makes sense because I'm computing distance traveled, which makes sense to measure in feet. So I'm going to come here. This is going to be a graph of these data points, and I'm going to show you how to draw in the trapezoids. All right, can you see these green dots? I'm going to draw in the trapezoids, and we're going to add up the areas of the trapezoids to approximate distance traveled here. So my inputs are time, my outputs are velocity, and my first trapezoid is going to cover, we said, cover the time interval from 0 to 2 seconds. So I'm going to take my 2 velocity values, which happen to be 0 and, is that 15 or 9? Imagine connecting them. This time when I connect my 2 velocities and then try to draw in the heights, since one of the heights was 0, it ends up looking like a triangle. You can still use the trapezoid area formula to compute it. I'm going to make the second trapezoid a different color. So I'm going to connect these 2 height values. You can see that trapezoid here. My third trapezoid, I'm going to connect those 2 height values. That's going to cover from 5 to 7. My other trapezoid is going to cover from 7 to 11. I'm going to connect those 2. 7 to 10. So I have 4 subintervals, which means I'm going to have 4 trapezoids. one's a triangle, and I'm going to add up the areas of these 4 trapezoids to find an approximation for distance traveled. So let's make sure we understand where that comes from. That's the sum of 4 different areas, the areas of 4 different trapezoids. So I tried to give you an arrow to show where each of the 4 comes from. So that first trapezoid is really a triangle. I'm multiplying the distance across, which is the difference between the left-hand side of the time interval and the right-hand side. So the difference between 0 and 2 is 2. So that's the distance across times the average of the heights. So this height, there was one height of 0 and one height of 9. So I've added 9 plus 0 and divided by 2. The second trapezoid I drew in red. You can see that the distance across is 3. That's where this 3 comes from. And the 2 heights are 36 and 9, so I've added 36 and 9 together and averaged and divided by 2. So you can see I've added up 4 trapezoid areas, and I get a final answer, which is the distance traveled is approximately 437.5 feet. Remember, each of these trapezoids has a width of something measured in feet. Nope. Minutes, right? Minutes, and then my velocity is in feet per minute, so minutes times feet per minute, the minutes cancel out, and I end up with feet. All right, so here's a great problem, because it reminds us that we've sort of lost our innocence here. It used to be that when I needed to compute distance traveled, I just multiplied velocity times time. Here I've been asked to find the area of a cross-section of a river. So just imagine a swimming pool. It has a depth, and the depth probably changes as you get deeper, but if you took a slice across one, direction of the swimming pool, the depth there is probably always the same. So if you wanted to find out the cross-sectional area of the swimming pool, you just multiply how wide the swimming pool is by how deep it is. So width times depth. That was fine, but now we're into problems where velocity could change. So if my velocity changes, I have to find the area under the velocity curve to find distance travel. Here, I can't just compute width times depth because the depth is changing. So really what I have to do essentially is find that area under the depth curve, whatever that would mean. So here, instead of just multiplying the width of the river, which we know is 24 feet, by the depth, I have to break that distance across the river up into little chunks and use an approximation. So I've been asked to make a trapezoidal sum with 4 sub-intervals. So I'm going to come to the table. My intervals are going to be starting at if the edge of the river is 0, from 0 to 8 feet, from 8 to 14, 14 to 22, and 22 to 24. And for each one of those distances across, I'm going to call that the width, and notice the depth is going to change. So here, if I'm using a trapezoidal sum, what I want to do is, for my first trapezoid, I'm going to have heights of 0 and 7, which I'll average. I'm going to multiply by the distance across that interval, which in this case is the difference between 0 and 8. Notice the depth is measured in feet. Distance from the edge of the river is measured also in feet. So I'm going to have units of feet times feet. So square feet. I'm going to add up square feet plus square feet plus square feet plus square feet. I'm adding area plus area plus area plus area. At the end, I'm going to have units of square feet, which I expected, which measures area. So I'm going to write up the calculation I'll do. All right, so notice that in each case, I try to set up the product, the area, in the same way so you can start to recognize it. This 0, this 0 to 8, that's a width of my trapezoid of 8. This trapezoid has a width of, the difference between 8 and 14 is 6. The next trapezoid has a width of 8, which is the difference between 14 and 22. The last trapezoid has a width of 2. And you can see here in the parentheses, I'm taking the 2 heights, so the 0 and the 7 and the 8, the 8 and the 2 and the 0, and the dividing by 2, that's me averaging the 2 heights. So we get an approximation of 115 square feet. You do need to know that if we're using a trapezoid approximation, we do have one case where we'll be able to say specifically how our answer is going to go, if it's going to be an overestimate or an underestimate. So I wrote the answers in there. I usually have to make this picture for myself. I don't usually remember just off the top of my head. So I drew a little function here that's concave down, And notice that if I try to draw a trapezoid across it, right, that trapezoid does not cover the whole area. The area of the trapezoid is an underestimate. So for a function that is concave down, a trapezoid approximation is an underestimate. Here I drew a little function that is concave up. And you'll see if I draw the trapezoid across the top, now this trapezoid is an overestimate of the actual area under that curve. So if f is concave up on an interval, a trapezoidal approximation is going to be an overestimate. So one last example, if I wanted to use 3 trapezoids to estimate the area under the curve of y equals x cubed from 0 to 6, I made a little picture here just in the first quadrant of y equals x cubed, and I know that if I'm going to cover the distance from 0 to 6 with 3 trapezoids, each trapezoid is going to have a width of 6 divided by 3, 2. Right? So I've made a little table here of the x and y values for this function, and I'll type in my answer. So there you go. So the distance across each trapezoid is 2. So these are the 2's that are the widths of the trapezoid. This 2, this 2, this 2. I'm going to take the average of the height, so 0 plus 8. The average I get by dividing by 2. So I have the 0 plus 8 plus 2 is the average of the heights. 8 plus 64 divided by 2 is the average of the heights. And I have 3 trapezoids. So my approximation is 360 for that area. And then the question here, is your answer an overestimate or an underestimate? Remember, for trapezoid approximations, the only information that helps us decide is if we can find out about the concavity of the function that we're finding the area under. So I have to think about y equals x cubed, at least in the first quadrant, that's concave up. So if I'm finding the area under a curve that's concave up, my trapezoidal approximation is going to be an overestimate. So I wrote this 360 as an overestimate because y equals x cubed is concave up. That's your only answer. So there are 5 problems from the book I'd like you to do. The couple at the end, they're related. Make sure that you're making a picture. For 5, 6, and 8, make sure you're making a picture. I'm going to look for your picture. And if you need a hint about how to make the graph of 2x minus x squared, so look at the degree. It's degree 2, so it must be a parabola. Look at the leading coefficient. The parabola is written in the wrong order. The terms are in the wrong order, so that's negative x squared plus 2x. So the leading coefficient is negative 1. That means the parabola has to open down. Look at what the x-intercepts would be for that parabola. Maybe use whatever you know about how to find the vertex and use that information to help you draw the picture. Then I want to see 3 separate pictures with the left rectangles, the right rectangles, and the midpoint rectangles drawn in.